Okay, now that particular picture that you see up there really isn't anything. Cole, you need to put that away and start focusing on electric line sports. Nate, you need to stop yawning at such a loud volume. No, this is a blank piece of paper that you're going to write on your own. That isn't really an electric field because it seems to be changing. I guess it could possibly be if there was a charge being applied that was then taken off and then being applied so on. It's basically just a cool picture that I put up there to see if I can hypnotize anyone. Some of this stuff you don't need to write down. So we've also already seen that electrically charged objects are able to exert force of attraction or repulsion on one another without these objects actually being in contact. What's that called? That whole forces without their contact called? What's that idea called? Anybody? No? Maybe?
A force field.
Action at a distance. Does it come up here? No, it's not.
Whoa.
Action at a distance. This is just kind of review, just to get you back thinking about this. Action at a distance. And I'll be posting these there. You do not need to write this all down. The notion of an electric field is used by science to describe how charged objects are able to exert force on one another from a distance, similar to the idea that the Earth's gravitational field is responsible for exerting an attractive force on objects near the Earth. So even though there's that separating distance in between, because this idea of a field is a scientific model, it explains how something can be in contact with the field, and thereby we can wrap our puny little human brains around the idea of there being a force. An electric field is thus defined as a region of influence around a charged object, and it can be made visible when small objects like grass seeds or pepper grains are placed near an electrically charged object. So, what is an electric field? It's simply a region of influence, a region where objects like grass seeds could possibly have a force applied to them. And we've talked about that already. It's in various handouts. You've seen it. I'm not going to ask you to define an electric field. What I will ask you to do is draw in these. Here's where you should begin to write. Sketch in the appearance of the electric field in the following cases. And you've seen some of this in a couple handouts, but let's just formally sort of take care of this. It is one of the outcomes. You must be able to draw in electric fields. What's the golden rule for drawing in electric fields? What do we use to test the direction of the electric field? A positive test charge. Very good, Gates. And so the electric field is the direction that a positive test charge would go. And so it would be repelled from that guy there, right? And that would be true throughout. And I won't make you draw too many. Okay, those are all arrowheads pointing out. Does it matter how long they are? No. Are these vectors? No. They look like vectors, Mr. Bennett. I know. They're not. They're arrows. They are, in fact, electric field lines. Now, if I were to double the charge on that, how would you then describe the resulting electric field? Would it be longer arrows? No, there would be more. They would, in fact, be closer together, a greater density, if you will. Is that what you said?
Yeah, I said it.
Good. Okay. What a wonderful test question.
Well, it is wonderful.
What I just said there, like if I doubled the charge, what would the resulting field look like? I'll have to remember to put it on the test. Now, what if you've got, so this is for what we, on the board there, I've got for a point charge, this is a point charge because it's a single object here. Over here, I've got 2 point charges. I've got a positive and I've got a negative. Regardless of where you put a positive test charge, it will be a repelled away from the positive and attracted to that negative, right?
These people are attracted. That's what I remember.
Yeah, you're kind of right.
I know.
What about like over here on the left? Would there be an electric field? Absolutely. And it would be which direction? away.
Up, up, and away.
And over here it would be towards. I will ask you on the test, drawing these electric fields. And you'll have to show me. I would expect to see this curvy thing in the middle. I would expect to see something over there on the left and something over there on the right. And again, if I were to create a greater charge, what if I only had like a greater positive charge? Well, it'd be more arrows over here. And probably over here you wouldn't probably see as much. Because this one, the one on the left is greater than the one on the right. I wouldn't worry about that too much, but that would be my answer. Would you learn in physics class today? Learn how to color, draw arrows.
Color with the pencil.
We learned that the basic unit of sociology is the what did he say? The person. Yes.
Mr. Bennett moron.
There are, it's kind of like antimatter. There's the morons. I think it was a student that came up with that joke for me once, and I just had to pass it on. The moron joke, yeah.
Oh, yeah.
Okay, so Gage, what does it look like?
Oh.
Broke my pen.
That's the
Mr. Bennett, which one's the herbivore?
They'll need plants.
Okay, I was wrong. No, you're right.
I thought you on pizza.
Okay, so away from positives, right?
Yeah.
Away from positives. What about in between? Yes. Because they're repelled. So something like that, right? And yeah, I'm going to be very flexible, very generous here with what yours looks like. If I see arrowheads pointing away, you're going to get it. Do I need to see the arrowhead itself? Absolutely, because if you don't have the arrowhead, I can't tell whether it's going away or
What
coming
about
towards.
arrowheads look like?
Mine aren't very good, are they?
Be careful.
There you go.
Here I have a positive on the right and a bar of negatives on the left. Yeah, away from positive, right?
Thought so.
Towards negative. Are these going to be pretty easy questions on the test?
No.
For the most part, yes, right? Now, I have to caution you. For the most part, almost in every situation, every problem that I give you on a test, generally I look for part marks, if possible. There really isn't part marks here. It's either right or wrong. If you don't know that it's away from positive and towards negative, if you get that backwards every single time, you could go from 8 out of 8 to 0 out of 8. Very easy to, well, completely wrong. So please, I'm begging you, make sure you get it right, away from positive and towards negative, right? Last one. I got a negative bar on the left and I got a positive bar on the right. From positive to negative. Now, what you get inside this one, and I should pause here for a second. What you get inside is a region of uniform density. Fancy talk for the lines are parallel. They are the same distance apart. You will get a slight little bend at the top and the bottom. Okay? But they are the same distance apart, which means, just put your pencil down for a second, just watch, which means right here and right there, the field strength is the same, generally. As you get closer, the lines get closer together and the field strength is greater. When you've got something like this, the lines are parallel and it's the same throughout.
Will there be anything on the outside?
There will be, yeah. Okay, but I want to make sure you get this. Usually, as you get closer to objects, the field strength gets closer, but because you've got a parallel plate capacitor here, The field strength is the same throughout, and it's the same strength far away or in the middle as it is right close. Does that make sense? Nod and say, yeah, okay, I get that.
Yeah, I get that.
Okay. He is asking about over here. Away from. Oh, sorry, not away from.
But would they still be parallel in the question?
Yes, I believe that they still are. Or, close enough. Right? So what I'm looking for in this diagram is that you've got the lines more or less parallel, and you've also got something on the left here and something on the right. It's because small objects seem to line up along certain lines that electric fields are often described by drawing electric lines of force as we've done above. This is a very good example of a scientific model. It's a way of describing something that we can't really see. A scientific model, electric field lines. You have this period to work on. It's an extra bonus one. You can use this period to work on the Millikan video. You can also use this period to work on the questions. Okay? I strongly urge you to use this period
Oh my god.
in the best way possible. All right.